Just want to point out here, we do have a short link for these slides, and I would definitely recommend you open that up and follow along at home, because we have a bunch of links kind of spread throughout here where you can go and learn more about all of this stuff. So first, who are we? So I'm Brian Hewlett, and I'm presenting here with my colleague, Robert. We're both, as Matthias said, we're both software engineers at Google working on cloud data flow, and we are both very involved in the Apache Beam community. So we've been working a lot recently on adding some new higher level APIs to the Python SDK, and that's what we want to show you today. So the agenda for the talk is, first, we're actually going to start right out of the gate with a live demo, and then we'll just go through really quickly, show you some demos of using all of these things, and then we'll come back in and show you more specifically how do you use these things, how can you learn more about them, and then finally, for people interested in the internals, we'll go into some details about how these things work. So let's jump over to the demo. So I have a Jupyter notebook here that I'm just running locally on my machine from running at Beam on head on master. And so the first thing we're going to do in this demo is just import Beam. And we also need to separately import the SQL transform and the Dataframe transform so that we'll be able to use those later on in some pipelines. And then this is the data set that we're going to be working with in these demos. So this is data that I've captured from a pub/sub public data set. So this is data that's constantly being streamed on a cloud pub/sub topic. That's basically simulated data that's simulated to look like the well-known New York City taxi rides data set, but it's actually in real time. And so I just captured some of that data and saved it off so that we can use it in some simple batch pipelines. So this is what the data looks like. It's just a series of events encoded in JSON. Each event has, some basic information like a ride ID, location, timestamp, how many passengers are in the taxi, that sort of thing. So we're going to run some pipelines on this. But the first thing we want to do actually is define a class that's sort of our data model representing what these data points look like. And I know a lot of Python programmers might balk at this. You might say, like, why are we making a class? Let's just use dictionaries. Why do we need to bother with this? But by taking the time to do this, you're actually sort of telling Beam about the structure of your data. And that's what allows you to be able to use these higher level APIs that we're going to be showing you today. So I defined this class, and it's basically, it just has a corresponding attribute and type for each of the fields in the original JSON data set. And then I actually registered that class with Beam as well. So then the first thing I'm going to do here is read in this data set and run it in a SQL transform. So I'm going to run this SQL query on it that's basically just doing a grouping aggregation. So we're grouping on the ride status field and getting the count of how many events actually have every corresponding ride status. So you see that came back, and there are just 3 different statuses. The vast majority of the events are these en route updates. So they're sort of like route updates as the taxi's moving along. And then we have a few, about 50 each, of both pickup events and drop off events. So that data volume kind of makes sense that there's only going to be a few pickups and drop offs, but a bunch more updates en route. So the next thing I want to do is run a SQL join, because this is one of the cool things that you can do with join or with SQL is you can concisely represent some joins. So in this SQL query, we are joining together 2 tables. One is the original taxi data set, and the other is this greetings table, which is actually just an in-memory P collection that I've made that just has 2 entries with a ride status and a corresponding message. So we want to join in for a ride status of a pickup. We want to send a message that says on my way, and for a drop off, send a message that says I'm here. So we're doing this join and then project out the timestamp field and the ride status itself and the actual message. And here you go. We print that out, and we got all these timestamps. And for every pickup, we get an on my way, and every drop off, we get an I'm here. So let's shift gears, and I want to do a demo with the Dataframe transform now. So the Dataframe transformer, again, we're processing that same data set. What I'm going to do is I made a P collection with that taxi rides data, and I'm going to call toDataframe on it. And what this does is it actually returns a pandas-like object. So it looks a lot like a pandas data frame, but it's not actually like a materialized data set that you can just print out and look at all of the data. But what you can do is start doing operations on it. And so you can do pandas-compatible, pandas-like operations on it. So you can index it based on some predicates. So like that's what I'm doing here is I'm filtering out where the passenger count is greater than 1 and the ride status is equal to drop-off. And then I can also do a projection in this pandas way. So I can select certain fields that I want to show. And then when we run that, you see we get those 3 fields, and we only get events where the ride status is drop-off and there are more than 1 passenger in the vehicle. Okay, so the last thing is actually kind of a surprise addition. This isn't actually even mentioned, I don't think, in the description of our talk, because it's something that we hadn't conceived at the time that we pitched the talk. But now we have this new feature that we want to show off, which is group by transform. And a group by is just a convenient way to for a convenient sort of Pythonic way for you to express grouping aggregations. So you can say, I want to group by a particular field and then do multiple aggregations on it. So in this case, we're grouping by the ride ID and then aggregating on the meter increments, or summing up all of the increments of the taxi meter counting up. And then we're also doing getting the minimum and maximum latitude and longitude to create kind of a bounding box of where this ride took place. And we print all that out, and you can see for each ride ID, we get the summed up meter increments and a corresponding bounding box for all of them. So there you go. That does it for the demo. I'm going to switch back over to the slides. So let's jump into how do you use all of this stuff and how are you going to learn more about it. So first off, we want to talk about Beam schemas, because that's a sort of prerequisite for all of this stuff. So all of these things we're going to demo, or we're showing you today, SQL transform, group by, and Dataframe transform, they require your input P collections to the transforms to have a schema. And this is something that will be familiar to Java SDK users, but it's a new concept in the Python SDK. And basically what a schema is it's, if you're familiar with in a SQL database, like a table definition in a SQL database where you just have an ordered list of columns that each have a name and a type, that's a schema. So it's a way of telling and describing the type of your structured data. And so your P collections in Beam, in order to use these transforms, need to have a schema attached to them. There are a few different ways that you can do this. So all of these schema-aware P collections, or P transforms, as we call them, will produce schema P collections, so that if you can chain them together in that way. But if you're starting from scratch and you want to add a schema to something else, you have a couple of options. You can use a named tuple class, like I did with the taxi points. And you can also use this beam.row construct. And I'll show you some detail how to use each of those. So the way the name tuple works is you just, you create a class that inherits from name tuple, and then you can put some attributes on it. And as you can see, this looks a lot like a table definition or a schema, where you just have an attribute name and a corresponding type for each one. And so from that, we are able, if you register this class with Beam, as we're doing here, then Beam is able to then interpret the schema from that. So then if you create a P collection that outputs that type, then that P collection will have a schema. And so we can plumb it into SQL transform or any of these other transforms. Similarly with beam.row, you can kind of dynamically create a schema. So for there, if you just have any old P collection, what you can do is plumb it through a Python function that produces calls this beam.row function and passes in keyword arguments. And so for each keyword argument, the name will be the name of your attribute. And we will actually use type inference to look at the expression you're assigning to it and figure out the type for it. So in this case, we can see that what you're assigning to recipe is always a string. And like is berry, that expression is a function that will always return a Boolean. So we're able to interpret the types or infer the types for your data that way. And then, again, this P collection will have a schema on it, and you're able to plug that into SQL transform or Dataframe transform. So we have these two options for how you can assign a schema to a P collection. And when you use one or the other is really up to you. The name tuple approach, kind of makes your types more explicit. It can be a lot better for documenting your code. You're making it clear what you're expecting and what you're going to produce. But the beam.row option, of course, can be a lot nicer for these sort of one-off dynamic declarations. And one thing I will say is that since the beam.row relies on type inference, like sometimes it might just kind of throw its hands up and say, I don't know what this is. I'll just call it typing.any. And then that can kind of cause problems if the transform you're trying to use it in needs you to be more specific. So then in that case, you might have better luck if you add a cast in, or you could just be more explicit by using the name tuple approach. Okay, so now we'll talk about how you can use SQL transform. So the SQL transform, again, it's one of these schema-aware P collections, or P transforms. So you can pass in any schema'd P collection, and then you just give it a SQL query. So it can be any valid calcite SQL query that can operate on that input P collection. Then you refer to that input P collection with a special table name where you just spell out P collection. And then from there, you can do any sort of projection, filter, grouping aggregations, whatever you can imagine to do with a calcite SQL statement. And then that's going to output a schema P collection for you. And then this schema P collection, if you don't want to use it, say in another schema-aware transform, you can also actually just process it natively with Python. So if this SQL transform produces two columns, one called Q and one called C, then in that output P collection, you could process that with a Python function by accessing the column names as attributes. So like row.q and row.c. The other option you have is you can pass in tagged P collections to the SQL transform, and then that way you can actually reference the P collection by name. So you can say just select star from A rather than indicating the entire P collection name. And similarly, you can pass in multiple P collections this way if you do a tagged P collection, and then you can actually do joins on them by referencing them from A join B, etc. The other option, or the other thing I wanted to talk about, is windowing. So you can't actually do windowing. You can't use the streaming SQL extensions very easily yet within the Python SQL transform. But what you can do is you can do windowing outside of SQL transform. And so then if you apply a window to your P collection, then everything that you process, all of your SQL will be processed within that window. And so for this, this can be really useful in a streaming pipeline. And so there's an end-to-end example of this in the Beam repo that's processing that taxi data set as well. So there are some limitations. The biggest thing is the limited type support right now. So what's available now in 2.23, in Beam 2.23, there's just a very basic list of types. We're going to get a few more in the 2.24 release that should be coming very soon. And the biggest limitation right now is you can't get timestamps in and out. And that's why you can't use the streaming SQL extensions easily. And so we hope to have support for that by 2.25. And then you will be able to do that. Another limitation is your field names that you produce in your SQL query need to be valid Python identifiers. So if you do just select count star, calcite is going to make up a name for that. And it'll probably look like this, $column1. And that's not a valid Python identifier, so that's going to cause problems when we try to follow on processing access that by attribute. So you just need to be careful that in those kinds of things, you reassign it, give it a name like count, something that will be a valid identifier. And the other thing about this is that it is a Java cross-language transform, so it's going to require you to have a Java runtime at pipeline construction time. And we'll talk a little bit more about how that works later. But for now, here are a few links in the slides if you want to go check out and learn a little bit more. And I'm going to hand it over to Robert to talk about group by.
Hello. So I'm going to talk a little bit about the group by transform. And kind of, if you recognize this name, it sounds a lot like group by key. And actually, by not specifying the key, it becomes a lot more flexible. So the basic shape of the group by transform is if I have a bunch of data, I could group by any predicate on that data. I can do a map function basically and say, I want to group these berries, these fruits, by the first letter of their name. And you might ask, well, what is this going to look like? And if you guessed something like this, that is exactly right. Our goal with group by transform is to be kind of intuitive and give you exactly what you want. So here, we grouped our things by the first letter, and we now have 3 groups, just as if you had done a group by key. So the group by transform can do more than this. You can actually group by multiple things at once. So here we're going to group by the first letter, and we're also going to group by this expression here of whether or not we think it's a berry based on its name. And the result is what you expect. Although here, since we provided keyword arguments to the group by transform, you're actually going to get a named tuple out as the key. So for instance, we have first letter S is very true, all the way down to first letter B is very false. And then on the right, we have this iterable of things that that fall into this group. So we can go further is if we have schemas. Schemas allow us to then identify these things we want to group by just by name. So here, if we create this kind of little tiny schema table, I'm going to say I want to group by the recipe, and then I also want to group by this expression is berry, and we get our result out. We have a name tuple of recipe and is berry, and corresponding to that tuple, then we have all the elements in our original P collection that satisfy this predicate that fall into this group. So one of the things when you're doing group by operations, kind of the next thing you are almost always reaching for is you want to aggregate by some other thing. So group by has this option, aggregate field. This is very similar to what we have in Java, is where you say, I want to group by this field, and I want to aggregate by this other field. And here I'm going to aggregate by the quantity field. Because we have schemas, we can just give it by its name. Then we say, I want to do a summation over that field. Here you can pass any associative callable, or you can pass any combined fund, basically anything that works in the combined per key, you can pass here. And then what you can do is you can say total quantity is the name of the output. And so the result is just this flattened table where we have our key, and then we have our total quantity. And this is kind of what one would expect. And we can actually group by multiple fields at once. This was shown in the demo. So we can say, I want to group by recipe and isberry. And at the same time, I want to aggregate the quantity, and I also want to aggregate this expression. I'm not limited to aggregating just fields that appear, and sum those up to get the total price. So we can have as many grouping fields and as many aggregating fields as we want. And the results are what you expect. We get this nice schema P collection that has per recipe and whether or not it's a berry, the total quantity and the total price, just like that. Now, this is something that we could have done otherwise. We could have done a map into the key part, which would be a tuple, and the value part, which would also be a tuple, and then a combined per key with the tuple combined fun. And then we could have had to follow this up with another map that kind of separates out the little bits into the little fields. But we find this to be much more cumbersome to express than the simple group by operation here. So that's kind of an introduction to the new group by operation that we think will be very useful. The other thing I'm going to talk about a little bit is Dataframe transform. So Dataframes kind of this concept of kind of taking the world of data science and data analysis by storm, and it's something that we want to offer to our customers of Beam. So the Dataframe transform looks a lot like the SQL transform. You say I have an input, and I want to apply a Dataframe transform to it, and instead of a SQL statement, I give it a callable that takes in a data frame and does some data framing operations to it. This isn't actually a data frame in the sense that everything here is deferred, but we figure out what we want to do. And then we output then another schema P collection. The operations that we do, we provide grouping and aggregation and those kind of things, and they induce a grouping on the whole data set underneath the whole P collection. And of course, lots of times what we want to do is more complicated than could be easily expressed in a single lambda. And so you can have this callable be outside, have closures, and we can even support things that have side effects. So in a data framing way, you might create a new column called C that is a combination of our B and our A column. And then we do some grouping operations, some filter, return the result. And this will then apply our input, this function, as if it were a data frame, and result in our output. So what are some limitations? As mentioned, all our operations are deferred. So in our function where we're doing these data frame operations, we can compute what the sum is, but we can't actually inspect that and say, branch, if the sum is bigger than 100, then do these operations, otherwise do those operations. Everything is deferred and then executed just like Beam pipeline at a later time. The other thing that restriction that we impose is that we must be able to infer the column set at construction time. So this rules out operations like transpose, where the data itself becomes part of the schema. These are usually not amenable to very large data sets that one would use with Beam, because if you had a schema that had 1 billion different columns in it, that'd be a little unwieldy. But we require the columns to be computable. And then the other thing we do is there are certain operations where it is difficult, if not impossible, to do those in a deferred manner. We want to support those as well. For instance, you might do some, some large-scale aggregation and filtering, and then have a small data set that works in memory. But we guard these operations by saying, for this portion of the pipeline, it's okay if you bring everything into memory on one machine, and just do the operations locally there. If you don't do this, you'll get an exception, which means that you won't accidentally do something that is non-parallel on your parallel data set. So we haven't implemented everything yet, but what is implemented under the hood is faithful to kind of the de facto standard for data frames, which is pandas. Because what we're doing is we're calling pandas under the hood. So all the little keyword arguments and everything will work just as they do in pandas. So lots of times, this is kind of the basic example. One wants to have more than one input, more than one output. So just like we did with our SQL transform, we can have two inputs, and these will be passed as two separate data framing things in our Lambda. We can do things by keyword argument. So if you have 10 different inputs, it's nice to be able to name them. And if you pass in a dictionary, then we will line things up in the callable. And similarly, we can actually have multiple outputs. So you say, given this input, I want to compute 2 or more things. And we can just use tuple unpacking to, on the right-hand side, we have our data frame expressions. And these get turned into actual P collections that are in the result. Finally, there's this, we can do keyword arguments as well. If you return a dictionary, you get a dictionary of P collections out. So finally, there's this last one, which is you can actually drop down into data framing mode by turning a P collection into a data frame with this two data frame operation, executing just as if it was a normal pandas data frame, and then you say to P collection to get a P collection back out and continue on with your Beam pipeline as before. So what's the status of this? This is currently in very active development. It's not ready for production use. We're targeting to have something stable by the 2.25 release. And you're welcome to try it out on master to kick the tires, see if this works for you, report bugs. The basic APIs and frameworks are in place, but pandas is a very big surface of fleshing out all the operations. Right now, one of the things we do is we divide up we're running against the pandas doc test to make sure that we're faithful. And we're dividing these things up into things that are skipped, meaning we haven't even looked at them yet, or won't implement something like transpose, where it doesn't make sense to do this in a parallel manner, and then passing. And currently, we have fairly good progress. We're passing almost half of our tests, and then we have a small number of won't skip, and then kind of a long tail. We've been looking, and there are obscure operations, but we think we have most of the basics there. We're also investigating things like read from CSV. There's a very convenient operations that Pandas provides. And we want to map those onto our IOs, but we haven't done this yet. So right now you have to read in your data as a P collection, then turn it into a data frame. So let's take a peek at how does this work under the hood? How exactly do we execute these data frame transforms? So as I mentioned, we have our input, which is a schema P collection, and we inspect the schema of this P collection to derive a proxy object of what our data frame should look like. What columns should it have? What types of those columns? And then in addition, we have a batching do fun to kind of batch these individual elements together into data frames that contain hundreds of elements for efficiency purposes. Then what we do is we create a deferred frame object that has all the same methods you would expect of a data frame, but doesn't actually execute them eagerly, but records them and builds up an expression tree. So let's look at this function right here. So we have a function that we saw before, and what we're doing is we're taking two columns, column A and column B, we're doubling column B, adding it to A and assigning it to C. And then what we're going to do is we're going to do a group by operation. We're going to group by the sum of C and then filter this out. And I guess I should have said C is less than 0 here, but that's okay. You get the idea. So now we want to apply this. Well, when we apply this, what happens? So what we do is we invoke my function with an actual data framey object, and we record and validate and return the expressions that were evaluated. So we build up this expression tree that kind of looks like this, where our original input is a placeholder, and we have two get column operations. We're getting A, we're getting B. The multiplication by B by 2 is then a multiplication. Our adding has two different data frame inputs. Then we have a set column, a group by, a filter, and a sum, and so on. So we get this tree that represents the operations that we need to perform to do this data frame. Now, if we look at this tree, we can kind of classify operations into 4 basic types. The first operations are element-wise. Element-wise operations map naturally onto PAR-do operations in a distributed system. You have a row, you do something to it, you get another row. This is easy to do in a distributed manner. Grouping operations are a little bit more complicated, they correspond to kind of the group by key and combine operations that one has in Beam and other systems. And one of the key insights to doing this efficiently is that if you co-locate all the things that are going to be grouped onto the same machine, then what we can do is we can invoke the underlying group by operations to efficiently perform the grouping and not worry about having missed out on some other grouping that is remote. We also lift combining operations when possible when we're doing these grouping operations. The third operation is we call them zipping operations. And these are kind of novel operations. They don't correspond very well to something that has a Beam native concept. They're a little bit like co-group by key or join. And they rely on the fact that for data frames, every data frame has an associated index. And this gives a natural one-to-one operation when one is operating on multiple data frames. The example here is we're adding two columns. And what happens is when you add two columns, it looks at the values that have equal indices across those two columns, and then kind of zips those together and adds the corresponding values to produce a new indexed data frame. And an essential optimization that we have here is if you executed a group by key or a join every time you want to do these zipping operations, it would get very expensive. So we're able to recognize when we're already indexed by the right thing to zip these things two things together. And this happens a lot. For instance, in our example, we took one data frame, we split out the columns, we did some manipulation, we zipped them back together. We don't have to do a shuffle because we know we're already partitioned in the right way. The last set of operations, we call them order-sensitive operations, things like iloc, where you're like, give me the fifth element of this data frame. And these are not yet supported because we don't have the notion of ordering in Beam. All P collections are inherently unordered, and we use hash partitioning for good distributions. So we've had some explorations in how we could explore this. If you declare your data frame to have an ordering, maybe then it makes sense to get the fifth element out of it, but we are not supporting these operations yet. So how do we actually execute this thing? So once we have this expression tree, we try to break it up into the minimal number of do funds and partitioning shuffles to actually execute this thing. So we break our graph up like this. On the left-hand side, we have something that's going to become one do fund, where we do some of the computation and a partial group by key. And then the right-hand side, we finish that grouping, take the total sum, and do a filter. We then group these into some do funds, and we inject a group by key operation that asserts the right partitioning of our P collection such that the group by keys, the group bys on the right-hand side make sense. And the basic idea is that we hash on the columns that we're interested in grouping by, we group by key, and then we can cat all the kind of pieces from all the workers that have the right hash into a single data frame to execute on the right. We then package these all up into our data frame transform. So the data frame transform has the batching operation at the head, and then it does this arbitrary DAG of operations to actually execute your data frame expression, and then it does some extraction and spits everything out on the right. So that, in a nutshell, is how the data frame transform executes. So now we'll go into under the hood on the SQL transform.
All right, thank you, Robert. Yeah, I'm going to be talking about showing you now how the SQL transform works under the hood. And I've adapted these slides from a presentation that my colleague Andrew Palau gave last year at the Beam Summit in Vegas. Yeah, I definitely encourage you to take a look at that if you want a little more detail on Beam SQL. We're just going to kind of scratch the surface here and talk about the specifics for doing this in Python. So Beam SQL is really heavily dependent on the Apache Calcite project. I mentioned it, we use the Calcite SQL dialect, and that's because we're using Calcite to parse our SQL and validate it. We also use Calcite to convert that SQL into a relational algebra or a logical plan, and then we use the Calcite optimizer to optimize it into a physical plan that we can then make into a Beam pipeline. And we also use a few other miscellaneous things from Calcite, like a JDBC driver that we use. And it also gives us implementations of built-in SQL operators, and as well as the ability to generate code for doing projections and filters. So that way we don't have to worry about generating the code ourselves. So the way this works when you're using the SQL transform from Java is you apply the SQL transform onto some P collection that has a schema, and you give it a SQL query. So then we send that information over to Calcite. So we send the information about the schema of the input P collection as well as the query itself. And then Calcite converts that query into an AST and then, or parses it into an AST and then validates it and then makes it into a logical plan, optimizes it into a physical plan. And finally, that physical plan comes back to Beam, which then we can map into a Beam pipeline. So we just do a basic mapping where the physical plan has relational nodes that we then map into P transforms. So like projection filters are pardos, joins become group by keys, etc. And then that pipeline can either be, we can send it off as an entire pipeline, or it might be just a subgraph that gets integrated into a larger pipeline. But either way, we're able to send this pipeline off to any of our Beam runners. So the difference when we are using this from Python is that from a Python pipeline, then you apply your SQL transform to some Python P collection and you give it a SQL query. So that all looks the same. But now what we need to do is it's a cross-language transform. So we need to call out to a Beam Java expansion service. And then what the Java expansion service does is it takes that P collection and does all of the same stuff. It applies the SQL transform with that query to it. And it goes through Calcite, the pipeline comes back. And then finally, then that pipeline comes all the way back into Beam Python, so then Python is able to integrate that subgraph of the pipeline with an overall Python pipeline. So then we end up with a pipeline that includes both Python operations as well as Java operations for the SQL portion. And so then we're able to send that pipeline off to any runner as long as the runner supports portability. So Flink and Dataflow and Spark all have portable runners that we can then send that pipeline off to, and we're going to run this Python and Java code at the same time. So one question here is, how does this work exactly? So from the Python side, we have this input P collection that we want to apply the SQL to, and then that needs to get over into Java, where it needs to apply this same SQL to some input P collection. So how is that understood by both Python and Java? And the answer is portable Beam schemas. So what we've done is we've actually defined a new standard coder that's called the row coder, and it's specifically for communicating structured data between SDKs in this way. So previously, all of the standard coders in Beam were specifically defined just for SDK runner communication, but now we have this new one that's really intended for this structured data SDK to SDK communication. And so this is what that looks like. So in the Java side, Java already had a very robust concept of schemas and rows. And so what we did was we took their implementation of row coder that was just a Java specific coder, and we codified that implementation as a standard coder, and wrote integration tests for it. So now there's a specification for it in the Beam model. And we also have an implementation of that specification in Python in the rowcoder.py file. And so then at construction time, this coder we're able to represent in a portable way and include the schema on it. So Python is able to say over to Java, this is what the schema of my data is. And then also at execution time, we have a portable way of encoding our rows so that we can actually transfer data between Python and Java and back. And then we can run these things concurrently as part of a Beam pipeline. And yeah, I believe that is it. So we can move on in case you all have any questions.
That was a really cool talk. Looks like you guys have invested a lot of time improving the life of the Python users. Awesome. And kudos to the demo as well.
Thank you.
There are some questions from the audience, so if you guys are happy to take them, I'll read them out loud, and then you can go ahead and answer them. That's fine.
Yeah.
So the first question is, can you create a schema and define a pipeline and then add data at a later time?
So I believe what that's asking, that is what we were doing in the demo. So, I defined this data model that defined the schema as I was building up the pipeline, but then the data wasn't actually defined until we ran the pipeline and it was reading it in. I'm not sure exactly if that's what that is asking.
That's how I interpret it as well, but maybe if the person in the audience can take it to like Worst
Yeah.
case.
So the only thing is that then the schema that you're defining needs to be compatible with the schema of the data that you're going to be inputting into the pipeline, of course.
Awesome. The second question was: Does this output to the portable universal? Does this output to the portable universal local runner?
Yeah,
Yeah.
so it works on the universal local runner just like any other portable runner. So you can run things locally, try things out, and then deploy it.
Yep.
Awesome.
And that's what we were doing in the demo. That was actually running on the portable ULR.
Cool. And then the last question for now is: When will group by and data frames be available via a cross-language expansion server?
Yeah. So group by is I think it's more of a kind of very surface level thing. So Java already has a group by, and Python has a group by, and Go to implement Go's group by would probably be make more sense in Go to whatever kind of is natural to Go than to try to make it cross language. As for the data frames, we have not yet looked at expanding that, but the we do have the infrastructure and tests for Java pipelines calling into Python. So it's just a matter of actually exposing that as a cross language thing. Our first target is to get it stable and ready, but I think that'll come soon after. So
Yeah, we'd also need to figure out what the interface for that would look like from another SDK, since it's very relies on defining a Python function. But that could be a cool thing to do for sure.
Yeah.
Awesome. I think that wraps up the session, and actually wraps up the day as well. So I want to thank you guys again for joining us, both you, Robert, and Brian, and the audience. Oh, there just came in another question. Are you guys happy to take that as well?
Sure, we'll take one more question.
Yeah.
Cool. Before the day ends, the question goes as follows: Have you thought about defining similar utilities for joining multiple P collections?
Is this probably in reference to the group by?
Yeah, I think so.
Yeah. A little bit of thought has been given there, but not too much. This is definitely something that would be worth exploring. It would probably be natural. Instead of just taking a P collection, you could just take a tuple or other kind of P collection. It might get a little unwieldy if you can't name things the same on both sides. So, for instance, a group by, and I could say group by recipe, and if both things had a recipe field, that would be a natural join. But if you wanted to express things like make the left-hand side be this, and the right-hand side be this, there's a question of whether we want to invent our own language or whether it'd be better to say, okay, if you want to express something complicated like that, use SQL or Dataframes that already have these capabilities. But this is definitely worth exploring. So yeah, good question.
Yeah, and on the Java side, I think they do have a similar utility like that. And there is like a join transform that you can input two schema P collections and join them that way. And it's actually using the same code that we use in SQL. So it might make sense to do something like that in Python.
Yeah.
Actually, while you were answering the question, another question came in. So, the audience is still awake. I don't know if it's the Europeans, but it's impressive. Currently, Beam Runner only have either Python or Java SDK. So would a runner now have both Python and Java SDK on them?
Yeah. So the idea with this is we're trying to move everything to the portability, and so we basically separate the language of the SDK from the language of the runner. So, for instance, with Flink and the local runner and Dataflow and Spark, what happens is the runner might be written in Java or C++ or Python, but we can execute things written in any SDK in any language. So as more runners are moving over to portability, they'll get this kind of thing for free, where they can just mix and match languages across any SDK's language, and don't have to be written in that language. So yes.
Awesome. Cool. Well, I think that really wraps up the day right now. So, yeah, thank you guys again. Thank you, everybody at home. And I'll see you hopefully tomorrow again.
Thank you.
Bye bye.
Thank you. Bye.